So the cool thing about my new setup is like, look, we're right there. Right there, that's Mel. She's sleeping. Shh, she's sleeping. We gotta do logarithms. We're gonna take a look at the properties of logarithms, and we're gonna be solving some logarithms as well, and exponential functions. So we'll be doing the both of those. So a quick overview of all the different logarithmic functions. You want to remember that the logarithmic properties are the same as the exponential properties. With exponents, if you multiply, that's the same as adding the exponents together. When you are dividing numbers with exponents, that's the same as subtracting the two exponents, because logarithms and exponentials are related to each other. And power to a power, multiply. These ones are a little bit trickier though. If you put a logarithm's base into it, it just sort of cancels the whole thing out. And you can do that same thing in reverse. We saw this last time, where if the logarithm ends up showing up, a logarithm of its base is not its base is down in the bottom. You kind of get it. You put a logarithm into an exponent, cancels everything out. If you put a 1 into a logarithm, it always spits out 0. And this is this again, where if you put in the base, you get 1. There's also the change of base formula. I downplayed this in pre-calculus. You can use it if you want. What you need to do is, it's a little bit backwards. You would think BM and then you would do BM, but bowel movement, gross. It's backwards the other way. So you need to do what's inside of the logarithm and divide it by the logarithm's base. You could also say, hey, the base has got to be on the bottom of the fraction, whatever you want to do to remember that. If you want to use it, you don't even have to use it. So we want to use these inverse properties to simplify this thing. So we've got a logarithm with its base put into it, because the base of natural log is e. So that thing just sort of cancels itself out, and we're left with, can I have a pen, please? Just whatever the exponent is, which in this case is x squared. Now we can use these properties in little goofy ways, where if I'm trying to find the natural log of 6, sure, I could type that into my calculator, but it's given me a couple things. So let's do some tricks. I know that 6 is 2 times 3. And since it's inside of a logarithm, I can break that up into 2 separate logarithms added together, ln of 2 plus the ln of 3. So I know what those are. They're up here. So I can just, sorry, my phone made a noise or something. I can just add those 2 decimals together, and then I know what the ln of 2 plus 3 is. It would be, let's see, 7, 1, that carries, and that carries, so I think it's 0, 8, 1. Oh, she's popped up. Oh, she's real excited. She wants to help. In the next one, we want to change that thing into an exponent, ln of 3 to the 1/2, and then we can bring that exponent in front. So 1/2 of the ln of 3, which is 1.0986. And then we just got to cut all that in half. So that's 5, this is 45, and then 9, and then 3. I might have done that slightly wrong, but you know what I'm doing. I'm taking the decimal and cutting it in half. All right. If you want to see another example where we're just doing this with variables, you can check out the PDF notes, but it's going to follow the same ideas. Next, I want to do a little bit of solving with these logarithm rules. So we had various tricks and tips for solving. What I'm going to use to solve for this first one is I'm going to use the translation rule. So I've got the ln of x equals 2. I can translate this into an exponential equation, e squared equals x. And then that thing is solved. I got to calculate what that is. I don't know what it is, so I'm just going to do it in Desmos. I got 7.389. It's approximately equal to x. She left. I think she just wanted to yell at me for talking while she was sleeping. She's like, I'm trying to take a nap. Why are you talking? In the next one, I want to get that thing out of the exponent. So I'm going to take the natural log of both sides in order to get that thing out. So then the x plus 2 comes in front. We've got an ln of e equals the ln of 8. So the ln of e, that's just 1, so it's gonzo. We got to subtract 2, so x is exactly, I'm going to do negative 2 plus, so it doesn't look like it's inside of the logarithm. Negative 2 plus the ln of 8. Let's do that on Desmos. And look at that, it even knows I'm doing logarithms. It's so smart. Oh, and I do want that negative. So we get 0.079. Done. If you'd like to see me solve another one, this one's kind of boring. I've got an interesting one that I'm going to do. You just need to get the bases to match, was one of our other tricks. So like this one where the bases already match, again, I'll do this on the PDF notes. When the bases match, you can just say that 3x equals the negative 4. Now this one's a little interesting, so that's why I saved this one for the video. We're going to solve this equation algebraically, and we're going to support our solution graphically. And actually, I'm going to do this a little bit backwards. Since we're going to look at that graph, I'd like to know what the answer is already so that I'm kind of prepared for when I get my actual answers. So I'm going to go into Desmos, and I'm going to type this thing in. I've got e, I'm going to type it in as y equals e to the x plus e to the power of negative x. If I type that correctly, e to the x, e to the negative x. And in our other equation, we're going to do y equals 3. So then we can see our two spots. We just care about where it equals 3. So my two answers should be negative 0.962, and my other one is positive 0.962. So I should get positive and negative 0.962. E to the x, e to the negative x. Okay, great. Okay, so excuse me. So the way I'm going to solve this thing, it wasn't quite done. What I want to do first is I want to get those e to the x's matches, and you'll see why two e to the x's to match, and you'll see why in a second. So I'm going to get e to the x plus, and this e to the negative x, I'm going to convert it into a fraction. The reason I want to do that is I'm going to use a substitution trick. So e to the x, I'm going to get sick of writing over and over and over again. So I'm going to substitute those for y's, and that'll make it a little bit easier for me to work with this problem. So I'm going to replace those e to the x's with y's and then continue solving my equation. It just kind of cleans it up a little bit. So the other solving things that we're going to be doing will be a little bit easier. We actually use this for derivatives. There's a u substitution form of derivatives that we do for calculus. So we're kind of practicing that right now. Now that I've got these, I want to get those two fractions put together. So I'm going to make that a y squared over y plus a 1 over y equals 3. Whoop. So we get y squared plus 1 over y equals 3. I'm gonna get rid of that denominator, so I get y squared plus 1 equals 3y. We get y squared minus 3y plus 1 equals 0. And unfortunately, this one we can't factor. So in order to solve this thing, guess what we're gonna have to use? Oh, it's time for the quadratic formula. Yeah, I haven't done that in a while. So quadratic formula, x equals opposite b plus or minus square root b squared minus 4ac all over 2a. So plugging stuff in, plug in. Mm-hmm. 4 times 1 times 1 all over 2a. So that's 2 times 1. So we get 3 plus or minus the square root of 9. No, that's not right. 9 minus 4, which is 5. All over 2. So let's go to our calculator, type that in. So we get 3 plus, I need a square root. Can you get out of the way, tools? I don't need you right now. Why would you go up there? I don't need you up there. Divided by 2. So I get 0.381 and 2.681, which you might have noticed when I said, is not my answer. But I was supposed to be getting, what were our points again? It was 0.96, negative 0.962, but we didn't get that. Well, remember, this is what y is. It is not what x is. We were trying to solve this thing for x. Remember, we replaced those y's with e to the x's. So we need to go back into that. I'm just double checking to make sure I didn't make any other errors. Well, make any errors, hopefully. All right, so we know e to the x equals, what was that gross decimal? 2.618. 2.618. So in order to solve this thing, we need to take the natural log of both sides. So let's do the natural log of that answer. And I think I can click and drag stuff around, or at least copy, maybe. Can I copy this down to there? Will you let me do that? No. Okay. And there we go. There's our 0.962. We also need to do the other one. It'll follow that same process. The ln of 0.381. And hopefully it should give us our positive one. Yeah. Well, I'm sorry. We already had our positive one. There's our negative one. So the natural log was getting both of those answers. So we got our plus or minus 0.964. Yeah, sure, they're a little bit off by a little bit. This graph is more accurate. I'm doing a bunch of rounding in this one. So that's why it's not perfectly matching up. But it's matching up pretty well. So plus or minus 0.962 is our answer. Six, 2. Sweet. So radioactive decay, let's do a little bit of a word solvy problem. So we want to use our growth rate again for this equation. So y equals our initial value a times our growth rate, which is b, and then we got our time, t, or x. Okay. So our y equals, there's an initial amount, so much, we got 8. And so what half-life is saying is that every time it completes that period, half of it is gone. So it is decreasing. We need to make sure that this growth rate is smaller than 1, and we're losing half of it each time. So I think it would be reasonable to use 1/2. Now it's doing this period every 12 hours. So every 12 hours, we want it to spit out a 1. And after 24, it should spit out 2. And if after 36, it should spit out 3. So whatever our time is, t, we want it to be divided by 12. Because remember, it should do 1 when it's gone 12 hours. It should do 2 of these halves after it's been sitting for 24 hours. It should do 3 of them after it's been sitting for 36 hours. That's why we're dividing. We want to figure out when there will be 1 gram remaining. So when 1 is our y value. So we've got 8, and we've got 1/2, and we've got t, and we've got 12. Now, don't be tempted to, well, you can be tempted, but don't do it. Multiply that 8 and 1/2 together. That 1/2 has got an exponent on it. We can't multiply those two together. I am going to get rid of it, though, by dividing by 8. So we get 1/8 equals 1/2 t to the 12. Now, I could do some logarithm stuff, but now I'm looking at that 1/8 and that 1/2, and I'm wondering, could I make those bases match? I bet I could, because if I do 2 times 2 is 4 times another 2, yeah, that's 3. So I can make these bases match and get a 1/2 cubed equals 1/2 t to the 12. Sweet. So then we can say 3 equals t to the 12. And hey, that was one of those things I kept saying. So when t equals 36. So after 36 hours, there will be 1 gram remaining. Hopefully you write better than I do. And I believe that is about it. Yeah, that's about it. So a reminder, you've got all of your sweet logarithms rules. You can use them to manipulate and move things around as you need. You need to make sure that you're keeping all these rules straight. They're the same as the exponential rules. Keep in mind the change of base formula, it's helpful, but it shouldn't be like your safety switch. It's something that you can do, but it usually ends up making more of a mess. So I try to avoid it. But we'll see. I don't know. I haven't done calc before, so it'll be something new. So thanks for watching, and catch you later.